All right, welcome everyone to this week's Autonomy Talk. This week is a pleasure to have with us Taylan Kargin, who is a PhD candidate in electrical engineering at Caltech, working with Babak Shibi. So something about Taylan, he got his bachelor's with a dual degree in electrical and electronics engineering and physics at Bill Kent University, and then got his master's in electrical engineering from Caltech in 2023. And he also has spent some time at Amazon. And his research sits at the intersection of control theory, optimization, and machine learning. And he focuses on developing reliable decision-making frameworks for large-scale autonomous systems, where these systems have to operate in complex and uncertain environments. His work is very interesting, and today is going to talk about non-rational infinite horizon control, presenting a framework for robust control and beyond. This is clearly a good fit for this series, and I am eager to hear more about it. And also feel free to ask questions during the talk. So without further ado, Taylan, the stage is yours. Go ahead.
Thank you very much, Jolie. Thank you for inviting me, and thank you for organizing this series. It's a pleasure to be here. Let me just quickly start with talk. So the talk, as Jolie mentioned, it's about non-rational infinite horizon control, and specifically about distribution robust control and further applications or extensions to mixed H2H infinity control. In this talk, I'm going to talk about distribution shifts a lot and distribution robust control. Distribution shifts are ubiquitous in real life. Whenever we have a real world system that we deploy our control system in it, and whenever the underlying model that we use, the nominal model, and the real world has discrepancies in their distributions, we encounter distribution shifts. So in just as a simple example, let's say we are designing a controller for an autonomous a car, a self-driving car, and we have and the car, let's say, operates in this complex real-world setting. And in this case, for example, what the controller could do is collect data from this world, from this environment, and from that data could construct a distribution, a nominal distribution about the world. But as soon as just due to the fact that we don't have perfect knowledge or perfect access to the underlying true distribution, which I denote here as P sharp, the constructed distribution P naught will be deviated from the underlying true distribution. So this is one source of distribution shift. So the goal in this talk that I want to discuss is how can we design controllers that are provably robust against distribution shifts. So I'm specifically going to focus on linear dynamical systems because we can actually come up with analytic solutions to these problems. And even specifically, I'm going to focus on fully observed, full information linear dynamical systems. So in this case, xt here denotes the state, and ut is the control input, and wt is the external disturbances. And a, bu, and bw are given matrices determining the dynamics. So this is standard LTI dynamics. And the controllers that I'm going to focus on are specifically LTI controllers, which observe the past disturbances up to time t and generate a control input at time t as a linear combination of these the past disturbances. And and specifically the controller is going to be time invariant. Because I'm going to focus on the infinite horizon setting later on. But even though this is the full information setting where the agent or the control agent observes the disturbances, all of these settings, all of these results can fairly easily extend it to partial information with output feedback. But I'm just going to focus on this full information setting for the sake of simplicity. And critical to this talk is a characterization of the disturbances. So the disturbance process, if we think of it as a stochastic process, it in general follows a distribution. It's going to be stochastic, but we don't know what distribution it follows. And also critical to this talk is that the disturbance process can be correlated in time. So now I'm not going to assume that the disturbances are going to be IID or so on. And so in general, I will keep this as general as possible. And also, of course, I'm going to assume that the cost is quadratic. And specifically, I'm assuming that it is quadratic in the state and the control input with positive definite matrices Q and R given to the controller. So just to, before I talk more about the distribution robust control setting, I will I will quickly review the two major paradigms in control.
What
So
shall we
these,
do? Shall I just
sure.
stick to your as you wait? As you wait. I'm the one who doesn't wait. If I go and sit down right now, it will take time. Wow.
Bennett, do you have a question? I'm not sure this was a question. Maybe Bennett was just unmuted. Anyways,
Okay,
in case you have a question, please raise your hand and we can take it.
Okay, so if there are no questions, then I can maybe move on. In these two major paradigms, we have stochastic setting, where the disturbances are assumed to follow a distribution, in this case, P sharp. And usually, and commonly, it's assumed that the distribution is perfectly known. And in this case, we can set the a stochastic control problem as minimization of the expected cost with respect to this distribution P sharp. And in the infinite horizon setting, we can also extend it by just taking the limit as the time the horizon goes to infinity. The other major paradigm is the adversarial robust control, where in this setting, the disturbances are not necessarily assumed to be stochastic, but they are assumed to be in an uncertainty set. And specifically in, for example, in the H infinity robust control setting, the disturbances are assumed to be either finite power or finite energy. And the optimization or the control problem then can be expressed as a min-max optimization problem, where we would be minimizing the worst case cost that is attained within this uncertainty set. And similarly, we can come up with the infinite horizon setting as well by considering the limiting case. And both of these paradigms have been studied very long in the past, and especially the stochastic control setting, the H2, LQR, LQG controllers have been already derived in closed form by Kalman in the 60s, and the H infinity controller was derived in closed form by Doyle et al. In 1988. So However, the real world is not necessarily purely stochastic or purely adversarial. We all most of the time have something in between. The disturbances or the environment usually has characteristics from both. And in this case, deploying a stochastic controller might be overly optimistic because it assumes perfect knowledge of the distribution, which is not the case, as we just discussed. And on the other hand, the adversarial robust controllers like H infinity controllers can be highly pessimistic and conservative because they completely ignore any statistical knowledge. So the question is, how do we actually come up with more realistic controllers and controllers that are robust to distribution shifts? So to achieve this goal, I'm going to consider ambiguity sets, distributional ambiguity sets. And a distribution ambiguity set is essentially an uncertainty set for the underlying distribution of the disturbances. So the stochastic disturbances are distributed by an unknown probability distribution P sharp, which is within a Wasserstein 2 ball around a given nominal distribution P naught. So a Wasserstein distance is essentially an optimal transport cost with quadratic cost function. And the radius here of the Wasserstein 2 ball essentially determines the level of confidence in the nominal model. So the smaller the radius is, the more confident we are in that the nominal model is a good representation of the underlying distribution. And if the radius is large, then we have less confidence about our nominal model. So in light of this, we can set up a distribution robust control problem, which is going to be basically a blend of both worlds, both the adversarial and the stochastic world. And specifically, in this setting, we're still considering the expected cost. But since we don't know the underlying true distribution of these disturbances, we consider the worst case expected cost within the ambiguity set. And the ambiguity set here is for any given finite time horizon t is similarly given by a Wasserstein 2 ball around a nominal distribution. And I'm assuming the nominal distribution is given to us. We have a nominal distribution, and we determined how well it approximates the true distribution, and which is determined by the radius r. And then we can come up with a distribution robust controller, which minimizes this worst case expected cost. So this is the finite horizon setting, and this finite horizon problem has been studied studied by Ta et al. In 2023. But in this talk, I'm specifically focused on the infinite horizon setting, where essentially we're basically taking the horizon to infinity, and we're looking at this time averaged worst case expected cost. So the advantage of distribution robust control is that it basically flexibly interpolates between the traditional stochastic LQG control and adversarial robust H infinity control, depending on the choice of radius. So just to go through the prior work, so the distribution robust control problems have been studied in the past. So this is not a new concept, but so far most of the works have focused mostly on the finite horizon setting. Or either they, even in the infinite horizon settings, the prior works usually assumed independence of the disturbances over time, which essentially simplifies the problem because we don't care about how We only have to care about one time step of the worst case distribution. But the more realistic setting involves should consider both time correlations and also the infinite horizon setting. The disadvantage of the finite horizon formulation, or why do we even care about infinite horizon, is that in the finite horizon case, the computation of the controller requires solving a semi-definite program, which scales with the horizon. So as even in my simulations, when I set the horizon to be 20 or 30, it takes about a minute to actually compute the controller. And this is not really feasible for real world application. If we have a real-time control requirement, then we cannot really solve an SDP in a moving horizon setting. This is very costly. So basically, overall, the finite horizon distribution of loss control is computationally prohibitive, and that's why we are interested in finding an infinite horizon controller. So before I explain how do we actually derive these controllers, I want to just show you some of the simulation results. So in this example, I'm showing you the power spectral density of the worst case distribution, or the autocovariance of the worst case distribution. So I'm assuming the nominal disturbance is a white noise. So it's IID Gaussian, let's say. And depending on the choice of radius, we get a different distribution. And in this example, all the worst case distributions are stationary Gaussian processes. So in that case, I can basically summarize the characteristics of the distribution by its power spectral density, or the Fourier transform of its autocovariance. So as the radius, when the radius is small, let's say here in this case 0.01, we are basically fairly close to the nominal, which is white noise. And if you remember, in the white noise, the power spectral density is flat at 1. And here we just have two little bumps, but we are fairly close. But as we increase the radius, we tend to get these peaks in the spectral density. And if you take the radius to even larger, you will see that these two peaks will converge to Dirac deltas, which will actually give us the worst case disturbance realization corresponding to the H infinity controller. And also, it's important to evaluate the time domain performance of these controllers. So in this case, I compared the finite horizon distribution robust controller and infinite horizon distribution robust controller under different disturbances. So in the white noise, which is the nominal case, we see that the distribution robust controller with the infinite horizon seem to actually perform better than the finite horizon controllers when the window is moving over time. So this is basically a model predictive control version. And the red ones and purple ones are basically the finite horizon, the average cost obtained from the finite horizon controller. And you can see that these controllers actually are not very stable, in the sense that they incur these bumps over time, whereas the infinite horizon controller provides stability, which is also another reason why we care about infinite horizon, because it provably guarantees stability. And similarly, when we test these systems and these controllers under different noise patterns, we see that consistently the infinite horizon controller actually performs better than the finite horizon controllers, and also provides more stable dynamics, closed loop dynamics. So this is an outline of my talk. So the rest of the talk will be it will a little bit more technical, but if you have any questions, please interrupt me at any time. So first, let me introduce the linear control setting. I'm going to use the operator formalism, and in this case, I'm going to represent the states and the control inputs and the disturbances as infinite dimensional vectors stacked together. And in this under this representation, the states is a linear function or a linear mapping from the control and the disturbances determined by these causal operators f and g. And these operators f and g are lower triangular or strictly lower triangular. They are infinite dimensional in both directions. And they are the elements of these operators are determined by the state space matrices A, BU, and BW. And as you can see, they're over the diagonals, they are constant, so they're toplets. This is because we are in the dynamics is time invariant. So these toplets operators are essentially convolution operators. And similarly, I can represent the controller as a toplets operator, a causal toplets operator, which is lower triangular, which maps the disturbances to the controller. So in the closed loop setting, we can come up with a closed loop operator, which maps the disturbances to the state and the controller. And we can write it in terms of the F and G operators of the system and the controller K. And all these operators essentially have frequency domain counterparts, and these frequency domain counterparts can be derived by the Z transforms. And in this case, we have these familiar expressions. And similarly for the controller, we have a Z domain counterpart obtained from the impulse response. And using this notation and assuming that the LQR cost matrices Q and R are identity, just for the sake of simplicity, we can rewrite the cost as a quadratic function of the disturbances and the control and the controller. So the first result that I'm going to talk about is basically a simplification of the infinite horizon control, a distribution of control problem, and assuming that the underlying nominal distribution P naught follows has a power spectral density, and I'm assuming that it is weakly stationary, and the power spectral density is denoted by m naught, which is also an operator with the power spectral density given by the Z transform. Then we can show that this complicated optimization problem involving limits, maximizations, and minimums is simply equivalent to this minimization. And basically what happens is that all of this limits, max, and expectation terms just reduce to a scalar optimization over a parameter called gamma. And here I'm defining the trace of these operators essentially as their integrals, the integration over the spectrum. And just to give you a sense of what H2 and H infinity norms are represented in this notation, they're essentially just the Frobenius norm with respect to this trace and the operator norm with respect to the same trace. So are there any questions about this? Okay. If not, then I will move on to the main result. So the main result is, the first part of the main result is that this complicated problem involving a trace and minimization over gamma, so on, can be shown to be equivalent to a min-max problem. And the reason that we're driving this min-max problem is because it is not clear a priori how to actually minimize this objective, which is convex over the controller. But in this minimax format, we essentially, at the expense of an additional maximization, we essentially simplify the problem a little bit. So before I explain how this simplification helps us, let me show you what this expression mean here. So BW here is the Buris-Wasserstein distance, and it's essentially the Wasserstein distance, or the optimal transport distance, between two stationary Gaussian processes following the autocovariances M and M naught. And what this tells us that we don't really need to care about the higher order moments. And only thing that we care about is essentially the second order moment, which is the covariance. And the reason is that the cost is nothing but quadratic in the disturbances. So when we evaluate the expected cost, we essentially see only the quadratic term of the disturbances. So that's why this whole problem of distribution robust control essentially reduces to robustness to the second order moment. So here is a proof sketch of how this works. So the main tool that I'm using here is the convex conjugate of this expression with respect to this closed loop operator. And the convex conjugate basically tells us that, or introduces, or characterizes this convex function in a variational way, and it linearizes the objective with respect to this quadratic term at the expense of an additional maximization. So and once we have that, we can essentially insert this back into the green expression, and we can swap the minimum and maximum because it's a convex concave program, and we essentially obtain the desired result. Of course, we have to deal with the minimization over this gamma parameter, but the gamma parameter essentially it acts like a Lagrange multiplier. And for any given choice of radius, there is a unique gamma, and we can always find or optimize over gamma by bijections. So that's why I'm only going to focus on the case with fixed gamma. And if we know how to solve this subproblem with respect to a fixed gamma, we can solve it for the general problem. So the second main result essentially characterizes the saddle point, meaning the best controller, the best distribution of us controller, and the worst case distribution. And I denote this by K star and M star. So assuming the gamma is fixed, and assuming for the sake of simplicity that the nominal distribution is essentially white noise, then we can derive the controller and the worst case distribution in closed form. And these expressions look maybe complicated, but I will explain in a bit what they actually really mean. here, just to explain what the terms here are, the delta is a lower triangular matrix or operator, and it's essentially the delta star delta or delta transpose delta is given by identity plus f star f. And this part relates to basically LQR Riccati equations. And this is a spectral factorization. And similarly, L star L star transpose is the spectral factorization or Cholesky decomposition of the worst case autocovariance operator M star. And here K and C is the best non-causal controller. But I'm not going to explain how to derive that exactly. So to give you a sense of the proof or how this derivation works, essentially we use first the duality in the sense that the min and max can exchange because of convex concave structure. And once we exchange the minimum and maximum, we realize that the minimization over the controller is essentially a quadratic optimization over the controller. So to give you a sense, in the beginning, we started with a complicated objective over the controller. But now, if we can solve, now we essentially can solve this problem by simply minimizing a quadratic objective and then maximizing over an additional dual variable, M, which is the worst case covariance matrix. So how can we minimize this quadratic objective? We can use what's called the Wiener-Hopf technique, which is a technique derived by Wiener-Hopf in the 1930s. And what it essentially means is that if we expand this quadratic objective, we realize that it essentially can be simply reduced to a projection in the Frobenius or H2 norm. And the projection is assuming that I plus f star f is taken factored as in the Cholesky factorization or spectral factorization, and similarly L star is the spectral factorization, and delta and L are lower triangular. And if I combine all of them, this term that you see here is always lower triangular because delta, K, and L lower triangular. So the minimum is attained by just taking equating this to the lower triangular part of this term. And essentially, the optimal solution is determined by this causal projection. And here the notation, the curly bracket plus and curly bracket negative essentially mean the causal or lower triangular part versus the anticausal or upper triangular part of an operator. So we derived all of these operator optimal controller and the worst case distribution in the operator notation. But how do we actually synthesize the controllers in a digital computer? So before I introduce the algorithm, I want to first show you that this entire characterization, which is infinite dimensional, has actually a finite dimensional representation. So when we take this worst case distribution and we use the frequency domain notation, it turns out that in the frequency domain, the worst case distribution it can be characterized by a finite dimensional parameter. So that finite dimensional parameter, which is denoted by gamma star, can be used to basically compute the worst case autocovariant or worst case power spectral density at any frequency point. This is because this entire expression is simply algebraic, and once I know the parameter, I can just plug it in and compute it at any frequency point at arbitrarily, so then basically what we need to do is to compute this finite dimensional parameter. So overall, what this basically tells us that this complicated infinite dimensional convex program over infinite dimensional operators essentially is a finite dimensional non-convex nonlinear program. And we know the analytic form or analytic expression of the optimal solution in terms of this finite dimensional parameter. So all we need to do is to compute that finite dimensional parameter. And the way I'm going to do that is through a fixed point iteration. So how it works is that we start with an initial estimate of the finite dimensional parameter, and we feed it to, and given that parameter, we can compute the worst case distribution corresponding to that parameter. And from that worst case distribution, or the power spectral density, we can compute its spectral factorization, which is the second step here. And from that spectral factorization, we can plug it in back to the formula that gives us the finite dimensional parameter in terms of the worst case distribution. And that gives us a new variable gamma. So iterating this over and over again gives us, it approximates the true underlying or the optimal finite dimensional parameter gamma, and plug it in back to the expression gives us the worst case power spectral density or the distribution. So overall, we can basically compute the worst case distribution or the power spectral density of the worst case distribution at any frequency to arbitrary fidelity. So even if we can compute the worst case distribution in the frequency domain, and also we can compute the controller in the frequency domain, we still have to implement this in time domain. And the main difficulty is that for any given arbitrary frequency domain controller, the resulting time domain controller might require infinite dimensional state space. The reason is that if the frequency domain expression or the frequency domain transfer function, if it's irrational or non-rational, then the underlying state space required to realize this controller will have to be infinite dimensional. So the only case when the optimal controller becomes a finite dimensional state space or admits a finite dimensional state space expression is if the transfer function is rational. But unfortunately, in this case, the underlying transfer functions, the optimal transfer functions of the both controller and the worst case power spectral density are irrational. And the reason is because of the square root. Even though what is inside of the square root is essentially a rational function, when you take the square root, it's not rational anymore. So therefore, the optimal controller, optimal distribution robust controller requires infinite dimensional state space realization. So therefore, we need to come up with a finite dimensional approximation in order to implement this in real time efficiently. So to do so, I'm going to approximate instead the worst case distribution by rational functions. So rational function approximation of or rational approximation of a positive definite spectrum essentially gives us another Gaussian process for the worst case distribution, which is generated by a finite dimensional state space. So to do so, let me introduce these polynomials. So P is here a positive definite polynomial, trigonometric polynomial, and Q is similarly a positive definite polynomial of scalar variable. And essentially, I need to come up with a rational function of the form P over Q, and P is a matrix polynomial, Q is a scalar polynomial. And I want this rational function to be as close to the worst case power spectral density over the frequencies, over all frequencies, and specifically for the worst possible frequency. And once I have such distribution, or once I have this approximation, then I can come up with a rational or state space realization for the worst case distribution. So this approximation, let's say if we want to approximate it up to tolerance epsilon, this can be equivalently represented as in terms of affine constraints. So that means and here all the variables p minus pk and qk are basically m degree are the coefficients of these polynomials, and all of this the entire expressions here are affine with respect to these coefficients. And what I can do essentially is that I can represent this as a linear program where I have to satisfy this for enough for a number of frequencies on this unit circle. And once I come up with a feasible solution or feasible approximant, then I can generate its spectral factorization, which is going to be a rational function, and then plug it in back to the expression involving the controller. We can see that the controller will become rational. And once the controller is rational, we can simply realize this controller as a finite order state space in a finite order state space controller. So how well does this rational approximation work? So in this example, in this plot, I'm showing you the controller over the frequency domain, and the optimal controller of the distribution, optimal distribution robust controller is plotted in color red, black, which is not even visible, and the approximants are with of degree 1, 2, 3 are plotted as well. So as you can see, if I approximate this by a first order state space controller, we get this blue curve, which is maybe not very good. But once I have second or third order, essentially the resulting approximate controllers overlap almost exactly with the true controller. And you can also see here the numerical values of how well the controller approximates for different choices of radius. And as you can see here, after maybe two or third order order approximations, we're essentially almost as good as the true non-rational controller. So, so before I move on to the more general setting, I want to pause a little bit and ask if there are any questions.
One quick question.
Yes.
The fact that your controller is irrational, does that mean that there's no finite dimensional linear state space representation? Or if you allowed yourself to have a polynomial time domain controller, you still couldn't get a polynomial time domain controller. Like,
So, are you asking if the controller is irrational, that there can be
the fact that the controller is irrational means that there is no finite dimensional linear state space controller that can implement it.
exactly.
Could there be a polynomial one, and therefore you should be trying to implement it as some sort of nonlinear polynomial time domain controller?
Yes, that's a good question. So that's a question I was also curious about, if it's just an artifact of restricting ourselves to linear controllers. But it turns out that the linear controllers are optimal, for example, when the nominal distribution is Gaussian. So we can show that linear controller is optimal anyways among all nonlinear controllers. So therefore, we don't actually lose anything by restricting ourselves to linear controllers. I hope this answers your question.
That would be true if the disturbances were Gaussian, but now that you've departed from the Gaussian case and you're allowing yourself to be in a Wasserstein ball from the Gaussian, then you no longer have that linear controllers are optimal necessarily.
Yes, so the result actually tells the following. If the nominal distribution is Gaussian, then the worst case distribution is also a Gaussian.
Okay, I missed that. Thank you.
Yeah. So then the linear controllers are essentially again optimal in that setting. But of course, if the nominal is not Gaussian, then one can also come up with maybe better controllers, nonlinear controllers. But in the simple setting of Gaussian nominal distribution, then you can show the worst case distribution is also Gaussian, and therefore the controller is the optimal controller has to be linear.
Thank you.
So just to give, so let me summarize the steps so far, and I will from there on generalize this machinery. So we started with a primal problem, and the primal problem we derived by getting rid of these limits and so on. And this problem is basically an optimization problem over the controller, and the objective is some complicated function of the controller. And to derive the optimal solution, we first obtained basically used the convex conjugate of this complicated expression and inserted it into the primal problem, and then exchanged the minimum and maximum. So in that case, we have an additional maximization to do, but now since we push the minimization inside, we can simply solve this minimization over the controller because it's quadratic minimization. And doing this in closed form, we get an expression of the controller in terms of the distribution or in terms of this power spectral density of the distribution, which is L star. And sorry. And again, also doing the maximization, and after you do some algebra, we also obtain an expression for the worst case distribution in terms of the controller. And from there, we notice that this the power spectral density of the worst case distribution is parameterized by a finite dimensional object, and the finite dimensional object perfectly determines the optimal solution. So then we essentially iterated over we essentially realized a fixed point iteration to compute the worst case to compute the finite dimensional parameter, which in turn gives us the worst case distribution and the best controller. And from that, we came up with the finite rational approximations of the worst case controller, which gives us a rational finite order state space controller. So this whole machinery can be generalized to essentially arbitrary convex infinite horizon control problems. So let's say you have an objective F, and this objective is convex, and you're trying to minimize this objective with respect to the controllers. And here TK star TK is the same as just a closed loop a transfer operator. When you take its transpose and multiply itself, it's a quadratic objective. Similarly, you can insert the convex conjugate or Frenchel conjugate of F into this expression, and then you get an additional maximization term. And this min-max problem is convex with respect to K, it is quadratic in fact, and it is concave with respect to the dual variable M. And exchanging these two, now we can minimize over the controller easily because it's a quadratic objective. And we do so by the Wiener-Hopf method, and we derive the controller in terms of the dual variable M, or its spectral factorization. And similarly, we can come up with the conditions for optimality for the dual variable through KKT with the KKT, and it essentially gives us another equation to find the worst case dual variable M in terms of the controller. So this gives us the saddle point. And once we have that, we can similarly show that the underlying optimal saddle points are characterized by a finite dimensional parameter. And we can utilize the same fixed point iterations and the same rational approximation methods to come up with rational controllers. So what are some examples that we can come up with? So the standard H2 and weighted H2 problems, which correspond to LQG under white noise and LQG under colored noise, essentially one example to these type of problems. And similarly, the standard H infinity problem is also another example. And we already know the optimal solutions for these problems and how to derive these. But essentially, we can use the same machinery to derive this the optimal H2 H infinity controllers by doing these iterative fixed point algorithm. And another example is the central H infinity controller, which is this expression involving logdet, and it corresponds to it has some relationship with risk sensitive control. And also we can use it to compute the risk sensitive control for arbitrary nominal distributions. So all of these problems have already been studied while in the literature, and the optimal solutions to these problems are known. What are some interesting problems that we can actually solve with this approach that have never been solved exactly before? So the two important examples that I'm going to focus on are the mixed H2 H infinity control and HP norm minimization. And HP norm is essentially any H, basically an LP norm that is between the L2 and L infinity norm. So that is another way to interpolate between the H2 and H infinity. But specifically, I'm going to focus on the mixed H to H infinity control, just because this is also a well-known problem. So the ultimate goal in mixed H to H infinity control is to minimize or find an H2 optimal controller which has an H infinity upper bound guarantee. So we're basically trying to find an expected cost minimizer with robustness guarantees. And in this case, you can express this as a multi-objective optimization, and you can come up with this Pareto front between H infinity and H2 norm. So the non-trivial case here is when the H infinity norm bound is between the best H infinity norm bigger than the best H infinity norm or the minimum H infinity norm, and it's smaller than the H infinity norm of the optimal H2 controller. So that case is non-trivial, and the other cases for gamma reduces to basically trivial solutions. So this problem was proposed first in 1989 by Bernstein and Haddad, but they didn't provide any solution. And afterwards there were many papers coming up that provided solutions for restricted class of controllers when, for example, restricted to fixed state space, fixed state feedback controller, and so on. But in '94, Migretsky basically showed that the optimal controller among all LTI controllers is non-rational. It has infinite order. But it didn't provide a closed form solution. It was just existential proof or proof that showed it is not possible to realize as a state space controller. So the exact solution has been unknown since 1989. And using this framework that I introduced, we can actually derive the exact solution in frequency domain in the closed form. And here, for example, I'm showing you the controller in the frequency domain. And here the blue curve is the optimal H2 controller. Red curve is the optimal H infinity controller. And these pink curves are mixed H to H infinity controllers at various levels of robustness. And as I decrease this parameter gamma, the upper bound on the H infinity norm, as it gets closer to the minimum H infinity controller, then we see that it flattens and gets much closer to the H infinity controller, but it still has some tails. And it turns out that as Migretsky showed, the true or optimal controller is non-rational, and you can see why, because this curve essentially is non-smooth, and if you have a non-smooth transfer function, it can't be a rational function. And we also derive rational approximations to come up with realizable state space controllers. And similarly, it turns out that using even like third order controller approximates the true mixed H to H infinity control or the optimal H to H infinity controller pretty well. So summary and conclusion, we derived we solved the infinite horizon Wasserstein distribution robust control problem, and we show that the true controller, optimal controller, is non-rational, doesn't have a finite dimensional state space realization. Then we proposed an efficient algorithm to compute the optimal solution in the frequency domain. And we also introduced an efficient rational approximation method to synthesize finite order state space controllers that approximate the optimal controller arbitrarily well. And later, we generalized this machinery of non-rational control framework to solve more general objectives, and we derived the exact solution for the mixed H-H infinity controller. And all of this framework that I introduced for control problem can also be extended to Kalman filtering and also to measurement feedback setting. And for future directions, I'm interested in extending this to online and adaptive control setting, where we in an online fashion we get to learn from the distribution, and we can update and refine the underlying ambiguity set as we learn more about the distribution. And I'm also interested in extending this to distributed control, because essentially if we can minimize, if we know how to solve distributed control problems for weighted H2 problems, then we can essentially extend this to arbitrary objective functions. And also other interesting directions are safety, introducing safety constraints, or also using the rational approximation method for model reduction techniques. Yeah, so thank you very much for listening, and happy to answer your questions.
Okay, Taylan. Thank you for your great talk. And Joel has left for a faculty meeting, and he asked me to host the Q&A session. Yeah, and there's a question in the chat saying that how does out of distribution entities are taken care?
So the out of distribution entities, I believe, essentially are taken care by. Let me go back. By this ambiguity set, because essentially, if you have an out of distribution example in the deployment that is not included or not part of your nominal distribution, then choosing this value R accordingly captures those out of distribution entities.
Okay, so any other questions? Okay, so we have already run out of time. So thank you so much today for your great talk, and it's very clear and very insightful. Yeah, thank you again.